welcome back to Sleepy Orbits. The lights are off, the day is finally behind you, and if your thoughts are still pacing around somewhere in the dark, that's all right. You're in the right place. Before you settle in, I want to hand you one strange, true thing to hold on to. Right now, above your roof, there are galaxies moving away from you faster than the speed of light, not in a theory, not in some distant future. Tonight, at this very moment, most of the galaxies astronomers have ever photographed are doing it. We were all taught the same rule. Nothing travels faster than light. Einstein wrote that rule down 120 years ago, and in all the time since, no experiment has ever caught the universe cheating. The rule holds. It always holds. And yet the universe breaks it every second, everywhere, on the largest scales that exist. But here's the thing most people don't realize. The speed of light was never a limit on the universe. It is only a limit on things moving through space. It says nothing at all about what space itself is allowed to do. And hidden inside that one quiet distinction is a real engine, written in real mathematics, published in real physics journals, refined for 30 years by serious people, that could, in principle, carry a human being to the stars without breaking a single law of nature. Tonight, the wall around our solar system is going to look a lot less solid than it did this morning. One thing before we begin. If you fall asleep partway through, good. That's the point. In the morning, tell me in the comments the last thing you remember hearing. And if you make it to the end, tell me which part of tonight's journey, past the speed of light, stayed with you, and what you'd like us to explore next. If these nights help you rest, a like or a subscribe helps this channel more than you'd realize. Now, let's begin. Light is fast in a way the human mind never fully absorbs. In a single second, a beam of light could circle the entire Earth 7.5 times. In the time it took you to read that sentence, light could have crossed the distance to the moon and come most of the way back. Sunlight, touching your window in the morning, left the surface of the sun 8 minutes and 20 seconds earlier. It crossed 93 million miles of empty space while you poured a coffee. Nothing we have ever built comes close. Nothing we have ever imagined building comes close. Light moves at 186,000 miles every second, and it has held that exact speed without slowing, without tiring, since the universe began. And yet, at the scale of the universe, light is slow, agonizingly slow. This is the first uncomfortable truth of the night, and I want to let it settle in gently. The nearest star to our sun is called Proxima Centauri. Its light takes 4.24 years to reach us. That means when you look at that patch of southern sky, you are seeing light that left before some of the people around you were born. And that's the closest one, the closest star in an entire galaxy of hundreds of billions. Our Milky Way is about 100,000 light years across. Light, the fastest thing that can exist, needs 100,000 years just to cross our own neighborhood. The next major galaxy over Andromeda sits 2.5 million light years away. When its light began the journey to your eyes tonight, there were no humans on Earth. There was no one to look up. Now hold those distances in one hand and hold this in the other. The fastest object our species has ever created is a spacecraft called the Parker Solar Probe. It was launched in 2018 and it reached its record speed by falling toward the Sun again and again, using the Sun's own monstrous gravity as an engine. At its fastest, Parker moved at 430,000 miles per hour. That is not a typo of the tongue. 430,000 miles every hour. At that speed, you would travel from New York to Tokyo in under a minute. It is the crowning achievement of human velocity, and it is less than 1/10% of the speed of light. Think about that for a second. Our absolute best, the fastest thing ever touched by human hands, does not even reach 1,000th of the universal speed limit. If the speed of light were a mile-long road, everything humanity has ever launched is still standing within the first 5 feet. If you pointed the Parker Solar Probe at Proxima Centauri and let it fly, the journey would take roughly 6,700 years. The entire span of recorded human history is about 5,000 years. Every pharaoh, every empire, every book ever written fits inside a shorter stretch of time than that one crossing. And our actual outbound spacecraft are far slower. Voyager 1, the most distant human object, launched in 1977 and now sailing through interstellar space, moves at about 38,000 miles per hour. If it were aimed at Proxima Centauri, which it isn't, it would arrive in a little more than 73,000 years. 73,000 years ago, our ancestors had not yet painted the caves of Europe. That is the shape of the prison. The stars are not hidden from us. We can see them perfectly. We simply cannot get there. Like a lighthouse seen from a rowboat across an ocean too wide to survive. So the obvious question is the one every child eventually asks. Why not just go faster? Build a bigger engine, burn more fuel, keep pushing. And this is where the universe reveals how strangely it is built. Because the speed of light is not like a speed limit on a highway, a number posted on a sign that a powerful enough machine could simply ignore. It is woven into the fabric of cause and effect itself. In 1905, Albert Einstein published the special theory of relativity, and inside it was a discovery that still unsettles physicists today. As an object moves faster, the energy needed to accelerate it does not grow steadily. It grows without limit. The closer you get to the speed of light, the harder each additional mile per hour becomes, until the mathematics demands infinite energy for the final step, not an enormous amount, not a galaxy's worth, infinite. We have tested this, not in thought experiments, but in machines. The Large Hadron Collider near Geneva accelerates protons using the energy supply of a small city. It pushes them harder than anything has ever been pushed on Earth. And after all of that, those protons travel about 7 miles per hour slower than light. 7 miles per hour. a gentle bicycle ride short of the limit, and no amount of additional power will ever close the gap. The machine can pour in more energy, and the proton simply becomes harder to push. The universe does not refuse loudly. It just quietly makes the last step cost everything, forever. And this is not a rule we take on faith from one machine in Geneva. Relativity is woven into your ordinary day, verified constantly, in places you would never think to look. Every time your phone finds your position on a map, it is consulting satellites whose onboard clocks run measurably out of step with clocks on the ground. Exactly as Einstein demanded. Fast by one amount because they sit higher in Earth's gravity, slow by another because of their orbital speed. The net error would grow by billionths of a second every day, which sounds like nothing until you learn that without the correction, your map position would drift by miles within a single day. Engineers build Einstein's equations into the satellites before launch, as routinely as they build in batteries. In 1971, physicists put atomic clocks on ordinary commercial airliners and flew them around the world. And when the planes landed, the flying clocks and the stationary clocks disagreed by exactly the whisper relativity predicted. Even the rain of cosmic particles striking our atmosphere confirms it. Particles called muons, born several miles up, decay so quickly that almost none should survive the trip to the ground. Yet, our detectors catch them constantly, because at their enormous speeds, their inner clocks genuinely run slow, and they live long enough to arrive. Time dilation is not philosophy. It falls on your roof. There is something almost tender about how absolute it is. Time itself bends to protect this rule. As you approach the speed of light, your clock slows relative to the people you left behind. Distances compress. The universe rearranges whatever it must, so that no matter how fast you go, a beam of light passing you still recedes at exactly 186,000 miles per second. Every observer, everywhere, always measures the same speed of light. It is the one fixed thing in a universe where everything else, even time, even distance, turns out to be negotiable. For most of the 20th century, that seemed to be the end of the story. The distances are unsurvivable, the speed limit is unbreakable, and so the stars belong to our telescopes but never to our children. Serious scientists said exactly that, in exactly those tones. Interstellar travel was filed away with perpetual motion, a dream that thermodynamics politely declined. Humanity, it seemed, had been born in a locked room with glass walls, and it was not for lack of trying. Before we go through the gate, it is worth spending a few minutes with the slow answers, the brute force plans, because they are magnificent, and because their magnificence is exactly what measures the wall. In 1958, at the dawn of the space age, some of the most brilliant physicists in America gathered around an idea called Project Orion. And the idea was this: build a ship the size of an office building, armor its underside with a colossal steel plate, and then detonate nuclear bombs behind it, one after another, riding the shockwaves like a surfer riding the apocalypse. It sounds like madness, and it was seriously, carefully engineered madness. Freeman Dyson, one of the great minds of the century, worked on it and believed in it, and the physics, remarkably, checks out. An Orion ship could in principle have carried thousands of tons and reached a few % of the speed of light. The project died in 1963 when the nuclear test ban treaty made exploding bombs in space illegal, and perhaps that was for the best. But mark what the maximum dream of the atomic age actually promised. A few % of light speed, a century or more to the nearest star, aboard a ship powered by thousands of nuclear weapons. That was the very best that brute force could imagine. 20 years later, the British Interplanetary Society tried again with cooler heads and better physics. From 1973 to 1978, their engineers designed Project Daedalus, the most detailed starship blueprint ever drawn. Daedalus would have been a fusion rocket, 54,000 tons at departure, almost all of it fuel, burning tiny pellets of exotic isotopes ignited by electron beams, hundreds of detonations every second for nearly 4 years. All of that fire, all of that mass, all of that engineering existed to deliver a payload of a few hundred tons to Barnard's star, 6 light-years away, in about 50 years. And here is the detail that tells you everything about the tyranny of the rocket. Daedalus could not stop. Carrying fuel to break would have made it too heavy to leave. After half a century of flight, it would have torn through the Barnard system in a matter of hours, cameras spinning, instruments screaming, and then sailed on into the dark forever. Its mission complete after a flyby shorter than a school day. 50 years of travel, 1 afternoon of arrival. That is what the mathematics of thrust and fuel does to dreams. Every pound of fuel must be pushed by other fuel, which must itself be pushed by more. And the equation compounds against you exponentially until the stars price themselves out of reach. You might think modern technology has softened this. It has not. The most serious interstellar effort of our own era is called Breakthrough Starshot, announced in 2016 with $100 million of funding and Stephen Hawking himself standing at the podium. Starshot's plan is the opposite of Orion's in every way, and its cleverness takes the breath away. Instead of a giant ship, build the smallest spacecraft possible, a chip the size of a postage stamp weighing about a gram, glued to a light sail a few yards across. Then fire a ground-based laser array with the power of 100 nuclear plants at that sail for a few minutes, accelerating it to 1/5 of the speed of light. No fuel aboard at all. The engine stays home. A fleet of these tiny glass butterflies could reach the Alpha Centauri system in a little over 20 years, photograph whatever worlds live there, and whisper the images home across a 4-year radio delay. It is entirely possible this happens within the lifetime of someone listening tonight, and if it does, it will be among the greatest things our species has ever done. And now look at it honestly, the way we have looked at everything else tonight. The fastest starship humanity can currently even sketch cannot carry a person. It cannot carry a sandwich. It is a camera the weight of a paperclip, and it still needs a generation to make the shortest possible crossing, and it, too, cannot stop, and its triumph will be a blurred photograph taken at 1/5 of light speed on its way past into nothing, a chip that cannot stop, a fusion titan that flies for 50 years to visit for an afternoon, a battleship that rides mushroom clouds. These are not failures of imagination. They are imagination performing at its absolute limit against the wrong side of the problem. As long as we insist on moving through space, the mathematics of the rocket and the wall of light, speed between them set the terms. And the terms are these. The stars may be looked at and pinged with our smallest possible machines and never, ever visited. For a species that crossed its own oceans in wooden ships, it is a strange and bitter clause, and it stood unchallenged in every engineering textbook on Earth, right up until people started paying proper attention to what the universe itself was doing. But here's where things get uncomfortable, in the best possible way. While engineers were fighting the rocket equation and physicists were proving that nothing can move through space faster than light, astronomers were discovering that the universe itself does not move through space at all. It does something far stranger. And the first hint of it arrived not from a machine or an equation, but from the light of distant galaxies carrying a message that took humanity years to believe. In the 1920s, a Belgian priest changed cosmology forever. His name was Georges Lemaitre, and he was both an ordained Catholic priest and a brilliant mathematical physicist, a combination that made almost everyone uncomfortable. In 1927, working through Einstein's own equations, Lemaitre found something hiding in them that Einstein himself had refused to accept. The equations did not describe a still universe. They described a universe that was growing. 2 years later, at an observatory in California, Edwin Hubble published the measurements that made it undeniable. Nearly every galaxy in the sky is moving away from us, and the farther away a galaxy is, the faster it recedes. Double the distance, double the speed. Triple the distance, triple the speed. The pattern held everywhere Hubble looked, in every direction, as if the whole sky was slowly leaning away from us. It is worth pausing on how hard that knowledge was won, because nothing about it was obvious. The raw hints had been piling up for years at a quiet observatory in Arizona, where an astronomer named Vesto Slipher spent night after freezing night gathering the faint light of spiral nebulae, hours of exposure for a single measurement, and found to his bafflement that nearly all of them were stretched toward the red, the unmistakable signature of recession. He had the clue as early as the 1910s, before anyone knew what the spirals even were. And the ruler that turned his clue into a map came from Henrietta Leavitt, a woman working at Harvard for 30 cents an hour, measuring the brightness of stars on glass photographic plates. She noticed that a certain family of pulsing stars beats in perfect proportion to its true brightness, slow pulse, bright star, every time. That one observation became the measuring stick of the cosmos. It is how Hubble proved the spirals were not clouds inside our galaxy, but entire galaxies of their own, impossibly far away, and it is how he charted their retreat. The expanding universe was not handed to humanity by a genius at a blackboard. It was assembled from frozen nights in Arizona and penciled columns in Massachusetts by people who mostly did not live to learn what their numbers meant. At first, that sounds like an explosion, with galaxies as the shrapnel flying through space. Almost everyone pictures it that way. Almost everyone is wrong. The galaxies are not flying through space away from us. The space between us and them is growing. This is the single most important idea of the night, so let's stay with it a moment somewhere quiet. Imagine a loaf of raisin bread rising in a dark kitchen. As the dough expands, every raisin drifts away from every other raisin, but no raisin is swimming through the dough. Each one sits perfectly still in its own small place, while the dough itself carries them apart. Distant raisins separate quickly, nearby raisins separate slowly, and the pattern looks exactly like what Hubble saw. The galaxies are the raisins. Space is the dough. Nothing is moving, and yet everything is getting farther away. And now watch what happens to the speed limit. Einstein's rule says no object can move through space faster than light. The galaxies obey. Locally, measured against their own patch of space, they drift at ordinary speeds, a few hundred miles per second at most. But the growth of the space in between is not motion through anything. It is the quiet swelling of distance itself. And there is no law anywhere in physics that limits how fast a distance is allowed to grow. The numbers are almost gentle at first. For every additional million light-years of distance, the expansion of the universe adds roughly 13 miles per second of recession speed. 13 miles per second is nothing, cosmically speaking, but it accumulates with distance, steadily, relentlessly, like interest. A galaxy 100 million light-years away recedes 30 times faster than one at 3 million. Follow the pattern outward farther and farther, and somewhere around 14 billion light-years from where you are lying right now, the mathematics crosses a line. Out there, the space between us and those galaxies is growing by more than 186,000 miles every second. Out there, galaxies are receding from your bedroom faster than light. This is not an exotic edge case. It is most of the universe. Astronomers measure cosmic distances by how much the expansion has stretched a galaxy's light on the way here, a quantity they call redshift. And in the standard model of cosmology, every galaxy past a redshift of about 1.5 is receding faster than light. That threshold is not far as the deep sky goes. The famous deep field images from the Hubble telescope and now from the James Webb, those photographs crowded with thousands of golden smudges, each smudge a galaxy of billions of stars. The majority of them lie past that line, which means most of the galaxies humanity has ever photographed are, at this moment, moving away from us faster than anything is allowed to move. Einstein's rule stands unbroken, and the sky is full of things outrunning light. Think about what that means for a second. We did not find the loophole in an equation. We photographed it. It hangs on the wall of every planetarium on Earth. Now, a question might be forming somewhere in the back of your drowsy mind, and it's a beautiful one. If those galaxies are receding faster than light, how did their light ever reach us? How can we see something that is outrunning the very thing it sends us? The answer is one of the loveliest ideas in cosmology. When a distant galaxy releases a photon in our direction, that photon is like a swimmer heading upstream in a widening river. Near the galaxy, the river of expanding space flows outward faster than the swimmer can swim, and for millions of years, the photon actually loses ground, carried backward even as it struggles toward us. But the boundary where the river runs at exactly light speed is not fixed. As the universe ages, that boundary moves outward. And so, a patient photon losing ground for eons can find one day that the river beneath it has slowed, that it has crossed into calmer water, and from there, it swims home to us. Some of the light landing in our telescopes tonight spent billions of years losing the race before it began to win. The universe is full of light like that, late light, light that should never have made it, arriving anyway. There is a soft warning folded inside this too. Because the expansion is accelerating, some galaxies we see tonight have already slipped past the point of no return. Their old light is still arriving, like letters from a friend who has already moved away. But nothing they send from now on will ever reach us, and nothing we send will ever reach them. The universe is slowly closing its doors. We covered that story fully on another night, the night about how most of the universe is already gone. Tonight, we only need the part of it that glows with possibility. And it is this: space itself is exempt from the speed limit. The universe has been demonstrating that exemption openly in every direction for its entire history. And if you think the expansion we can see is impressive, the universe once did something so much more violent that it makes today's expansion look like stillness. To find it, we have to go back to the very first fraction of the very first second, all the way back to the beginning. In 1980, a young physicist named Alan Guth was studying a stubborn set of problems in cosmology. The universe, when we measure it carefully, is strangely uniform. Take its temperature in one direction, then turn around and take it in the exact opposite direction. Regions separated by the entire width of the observable universe, and the readings match to 1 part in 100,000. That should be impossible. Those two regions have never been in contact. Light itself has not had time to cross from one to the other since the beginning, so nothing could have evened out their temperatures any more than 2 cups of coffee poured in different cities could settle to the same warmth. And yet the universe is the same everywhere, as if the whole sky once agreed on everything and then was pulled apart before it could change its mind. Guth's answer, published in 1981, was called inflation. And it says exactly that. In the first unimaginable instant, the regions that now sit on opposite sides of our sky were close enough to touch, close enough to mix, close enough to agree. Then space itself expanded, not gently, like today, all at once, in a burst beyond every metaphor, in a sliver of time almost too small to write, from about 1/1,000,000,000 of 1/1,000,000,000 of 1/1,000,000,000 of a second after the beginning and lasting only a few instants more, the universe grew by a factor of at least 100 trillion. Regions separated by less than the width of an atom were flung apart to distances measured in light years. Space, in that moment, was expanding not at twice the speed of light, not at 1,000,000 times the speed of light, but at multiples that have no name and no useful comparison. And here is the point that matters for tonight. No law was broken, not one. Nothing in that primordial fury ever moved through space faster than light. Space itself simply grew monstrously and carried everything with it, and Einstein's rule slept through the whole event undisturbed, because the rule was never about space. It was only ever about things in space. So let the picture assemble itself slowly, the way a room assembles itself when your eyes adjust to the dark. The universe began with an act of faster-than-light expansion. It continues that act tonight at the far edges, where most of the galaxies we know are receding beyond light speed even as you breathe. The loophole is not a trick waiting to be invented. It is the oldest behavior the universe has. The only question, the question that waited quietly through all of human history until 1994, was whether the trick could ever be done deliberately, not to a universe, to a ship. In the early 1990s, a young Mexican physicist named Miguel Alcubierre was working toward his doctorate at the University of Wales in Cardiff. His field was numerical relativity, the art of teaching computers to solve Einstein's equations, which are so difficult that in most situations no human can solve them by hand. By day, he studied the mathematics of curved space-time. By night, like millions of other people in the early 90s, he watched Star Trek. And at some point, watching that fictional starship slide across the screen with the word warp glowing on its displays, Alcubierre asked himself a question that sounds like a joke and is not. Could the equations of general relativity, the real ones, the ones tested to exquisite precision, actually permit something like that? Understand what he was really asking. He was not asking whether we could build it. He was asking whether the universe's own rulebook forbids it. Those are profoundly different questions. The rulebook of physics forbids many things absolutely. It forbids perpetual motion machines. It forbids engines that run on nothing. It forbids accelerating a rocket past light speed, as we saw, with an infinite wall of energy. If faster than light travel belonged on that list, the mathematics would say so, and the dream would be over, cleanly and forever. So Alcubierre went looking, And in 1994, in a short paper published in the journal Classical and Quantum Gravity, he announced what he had found. The dream was not on the forbidden list. There is a configuration of space-time, a legitimate exact solution to Einstein's equations in which a region of space can travel faster than light, carrying a ship inside it, without the ship ever moving faster than light through space. He called the paper The Warp Drive, taking the name directly from the show that inspired it. It remains one of the very few times in history that science fiction handed physics a question, and physics, after checking carefully, answered maybe. Here is what Alcubierre's solution actually does, and I want to walk through it slowly because it is one of the most elegant ideas ever written down, and because you have already met every ingredient it uses. Picture a small, flat pocket of ordinary space, a calm bubble with a ship resting inside it. In front of the bubble, space contracts. The distance between the bubble and its destination is continuously destroyed, eaten away, mile after mile, simply removed from existence. Behind the bubble, space expands. The distance between the bubble and home is continuously created, mile after mile of fresh space poured into the wake. The bubble and the ship inside it is carried forward the way a raisin is carried by rising dough, the way a distant galaxy is carried by the expansion of the universe. The ship's engines are silent. The ship does not move at all, in the only sense of moving that physics polices. It sits perfectly still inside its pocket of calm, while the geometry of the universe flows around it like a river around a leaf. Inside the bubble, there is no acceleration. No force presses the crew into their seats because in their local patch of space, nothing is happening. They are in free fall, weightless and serene the entire journey. Outside the bubble, an observer would watch it cross the sky at 5 times the speed of light, or 10, or 100. The mathematics places no upper limit on the bubble's speed, none. And Einstein's rule remains perfectly intact, because the rule constrains motion through space, and nothing here moves through space. The distance ahead is not being crossed, it is being deleted. If that feels like cheating, hold it against what you learned earlier tonight, and notice that it is not even new. Galaxies beyond redshift 1.5 are separating from us faster than light at this very moment, carried by expanding space, breaking no law. The infant universe inflated at speeds beyond all language, breaking no law. Alcubierre's insight was not to invent an exemption to physics. It was to notice that the exemption already exists, has always existed, and to ask whether it could be made small and local and pointed. The warp drive is nothing more than the oldest behavior of the universe miniaturized. Expansion behind, contraction ahead, and a still, quiet room in between, falling toward the stars. The consequences read like poetry disguised as physics. A ship riding such a bubble to Proxima Centauri at 10 times light speed would arrive in about 5 months, not 73,000 years, not 6,700 years. 5 months, roughly the length of a school semester. And because the crew never moves through space at high speed, the strange time distortions of relativity never take hold. Their clocks run in step with the clocks at home. They would return from the round trip having aged the same 10 months as everyone who stayed behind, stepping off the ship into a world that still remembers them, greeting children who are still children. Relativity's cruelest tax on travelers, the one where a fast round trip returns you to a home grown old without you, in some versions centuries older, is simply never charged because the tax applies to motion through space, and they never moved. When the paper appeared, the physics community did something revealing. It did not laugh. Reviewers checked the mathematics, and the mathematics was sound. The solution was real, exact, and legal. Within months, other relativists were extending it, probing it, publishing responses in the same serious journals. The word warp, which had lived its whole life in fiction, quietly entered the index of peer-reviewed physics, where it remains today. Whatever this idea is, it is not a crank's fantasy. It is a citizen of general relativity, born with full papers. And it matters enormously whose equations these are. So let's take a breath and remember the theory's record, because everything tonight rests on trusting it in strange territory. General relativity has never once been caught in an error. Not once in 110 years. It began by explaining a tiny, maddening wobble in Mercury's orbit that had defied astronomers for decades. In 1919, it predicted that the sun's gravity would bend starlight by a precise amount, and an expedition led by Arthur Eddington photographed a solar eclipse from the island of Principe and caught the stars out of place by exactly that amount, the result that made Einstein famous overnight. It predicted black holes before anyone believed in them, and we have now photographed their shadows. It predicted that cataclysms in deep space would send ripples through space-time itself, and in 2015, a pair of detectors in Louisiana and Washington felt the tremor of 2 black holes colliding over 1 billion light-years away, a wave in space thinner than 1,000th the width of a proton, arriving on schedule, shaped as promised. Every wild thing this theory has ever claimed, and its claims are the wildest in science, has come true under oath. So, when the same equations calmly assert that a bubble of space can outrun light while its passenger sits still, that assertion cannot be waved away as fantasy. The most reliable witness physics has ever produced is on record saying the geometry works. What remains in dispute is only the fuel. But Einstein's equations have 2 sides. One side describes the shape of space-time, and that side Alcubierre had sculpted beautifully. The other side describes what must fill space-time to produce that shape. Every curvature has a price, payable in matter and energy, the way every dent in a mattress requires a sleeper of a certain weight. When Alcubierre computed the price of his bubble, the equations returned something that no laboratory, no star, no galaxy has ever contained. To hold the bubble open, the wall of the bubble must be built from negative energy, Not low energy, not weak energy. Energy less than nothing, less than the empty vacuum itself. A substance physicists politely call exotic matter, a phrase that means, roughly, we have never seen this, and we are not sure the universe stocks it, and the amount. In the original configuration, a bubble big enough to carry a small ship demanded a quantity of negative energy whose magnitude exceeded the total mass energy of the entire observable universe. Not by a little, by a factor of about 100 billion. Every star, every galaxy, every atom of gas and mote of dust in the visible cosmos, all of it converted to pure energy, multiplied 100 billion-fold, and then somehow rendered negative. That was the entry fee. The universe had answered Alcubierre's question with a strange and very cosmic sense of humor. Yes, the door exists. Yes, it opens. And the key weighs more than everything. For a lesser idea, that would have been the obituary. But something interesting had happened the moment the paper was published. The question had changed shape. For a century, the question was, is faster than light travel forbidden? And the answer was, apparently, not. Now the question was merely, how expensive is it? And expense is a different kind of problem. Forbidden never budges. Expensive can be negotiated with. Physicists are, by temperament and training, hagglers. And for the last 30 years, in journals and conference halls and late-night calculations, they have been haggling the universe down. The first thing to say about negative energy is that it is not pure fantasy. This surprises almost everyone. In 1948, a Dutch physicist named Hendrik Casimir predicted something absurd sounding about empty space. Take two flat metal plates. Polish them until they are nearly perfect mirrors. Bring them close together in a vacuum, closer than the width of a human hair, and do nothing else. No charge, no current, no magnets. According to Casimir's calculation, the plates will be pushed together by the emptiness itself. The reason lives in quantum mechanics. What we call vacuum is not truly empty. It seethes everywhere and always, with fleeting quantum fluctuations, fields trembling at every possible wavelength, appearing and vanishing too quickly to be caught. Between the two plates, the narrow gap cannot fit every wavelength, the way a small room cannot hold every note of an organ. So the space between the plates trembles slightly less than the space outside. There is less nothing between them than around them, and that imbalance presses the plates together gently, measurably, really. The effect was confirmed in the laboratory decades later with exquisite precision. Here is the part that matters for our story. In the mathematics, the energy density of the region between those plates is negative, lower than the vacuum, less than zero. Nature, it turns out, does keep negative energy in stock. It simply keeps it in the smallest denominations imaginable, in quantities so faint that no one has ever gathered enough to do anything with it. And quantum theory itself appears to impose strict rules about how much can be borrowed, for how long, and where. So the exotic ingredient of the warp bubble is not forbidden. It exists. It has been measured. It is just unimaginably scarce, which returned everyone to the true obstacle, that opening entry fee, 100 billion universes worth. And this is where the haggling began, and where the story becomes, I think, genuinely moving, because you can watch 3 decades of human cleverness pushing against a single number, and you can watch the number give ground. The first great concession came in 1999 from a Belgian physicist named Chris van den Broek. His insight sounds like something out of a dream, and I mean that almost literally. Einstein's geometry permits a region of space to be larger on the inside than it appears from the outside. That is not a metaphor. Curved space-time genuinely allows a pocket whose interior volume is vast, while its external mouth is microscopic. Van den Broek redesigned the warp bubble so that only a tiny external bubble, smaller than an atom on the outside, needs to be wrapped in exotic energy, while the inside of that bubble balloons out into a hold big enough to carry a ship. Keep the expensive surface small, keep the useful volume large. With that single act of geometric origami, the negative energy requirement collapsed from 100 billion universes to roughly the mass of the Sun. Let me say that again, because the size of the step is the whole point. One idea, one paper, a few pages of mathematics, and the price of the impossible fell by a factor so large it has no everyday name. From everything that exists, multiplied 100 billion times, down to one star, still hopeless, still a sun's worth of a substance we can barely make a whisper of, but hopeless in a new and smaller way. Then the number kept falling. Through the 2000s, relativists learned that the energy cost depends enormously on the thickness of the bubble wall, on the shape of the warped region, on how the field is arranged. In 2011 and 2012, a NASA engineer named Harold White, working at the Johnson Space Center in Houston, presented calculations suggesting that reshaping the bubble's cross-section into a rounded ring, a donut of warped space rather than a thin shell, could shrink the requirement again, spectacularly. By his estimates, a modest bubble might need negative energy equivalent to the mass of a car or of a small spacecraft. The number usually quoted is around 1,500 pounds, roughly the mass of Voyager 1 itself. His figures were debated, and they remain debated, but pause on the trajectory rather than the endpoint. In 1994, the price was 100 billion universes. By 2012, serious people at NASA were arguing about whether it was closer to a truck or a probe. The wall between us and the stars was not holding steady. It was thinning, decade by decade, under nothing but thought. And then came the discovery that changed the tone of the whole field. In 2021, a physicist named Eric Lentz, working at the University of Göttingen in Germany, published a new class of warp solutions built from structures called solitons. A soliton is a wave that holds its shape as it travels, the way certain canal waves can roll for miles without breaking apart. Lentz found soliton-shaped configurations of space-time overlooked for 27 years that could, in principle, carry a region faster than light. And here is the sentence that made physicists sit up at their desks. His solitons required no negative energy at all, positive energy only, ordinary energy, the kind stars and planets and power grids are made of, arranged in an extraordinary pattern. In the same journal where Alcubierre had published the original dream, Lentz published a version of it that dispensed with the exotic ingredient entirely. In his calculations, the fields could even be sourced by a plasma of the sort physics laboratories already create. The energy quantities were still absurd by engineering standards, the mass energy of hundreds of planets for a small craft. But notice what quietly left the conversation. For the first time, the discussion of faster-than-light travel no longer depended on a substance that might not exist. The question had shifted from whether the universe permits the fuel to merely how much of it is needed, and how much has been falling for 30 years. Then, in 2024, a team at a research company called Applied Physics, led by Jared Fuchs, passed another milestone, and this one deserves to be described carefully because it was widely misreported. Working with a numerical toolkit they built called Warp Factory, software that lets physicists assemble and stress test warp geometries inside a computer, the way engineers crash test cars before building them, the team constructed what they called the first physical warp drive solution. A warp bubble that satisfies every one of the energy conditions of general relativity. No negative energy, no borderline cases, no fine print. A shell of ordinary, positive energy matter arranged so that it carries a flat pocket of space along with it, with everything inside behaving exactly as the Alcubierre geometry promises. Published, peer-reviewed, in Classical and Quantum Gravity, the same journal once again. The catch, and it is a real catch, is that their solution is subluminal. It cruises below the speed of light at a constant velocity and cannot yet accelerate on its own. It is not the starship. But understand what it is. It is a warp bubble made entirely of ingredients the universe actually sells. The geometry works. The pocket of calm, carried through space by sculpted energy, is now, on paper, physical. Since then, the frontier has kept moving in both directions at once, the way real science does. In 2025, a physicist named José Rodal described warp geometries that push superluminal designs toward almost entirely positive energy, shrinking the exotic remainder to a thin deficit. And newer verification tools applied ruthlessly have found small leaks in some earlier positive energy claims, tiny violations hiding in the numerics. And one recent analysis argues that warp fields may suffer a deep-seated instability that no one has yet designed around. I want to be honest with you about that tonight of all nights, because this channel does not sell certainty. Nobody has drawn the blueprint of a starship. What has happened is quieter and, in a way, larger. Faster than light travel has become a working research field with journals and software and rival camps and honest referees, a field where the central question is no longer permitted or forbidden, but merely and endlessly how much and how. 3 decades of haggling, from 100 billion universes to 1 star to 1 truck to 0 exotic matter at cruising speed. The universe, it seems, was never refusing, it was negotiating. So now let's do what this channel does best. Let's stop analyzing and go aboard. For the next little while, I want you to stop being a listener and become a passenger. Physics has told us in surprising detail what riding a warp bubble would actually be like, and almost none of it matches what the movies taught you to expect. Close your eyes if they aren't closed already. You have a ticket for the first crossing to Proxima Centauri. The year doesn't matter. Call it someday. The ship is smaller than you imagined because it needs no fuel tanks, no vast engines, no shielding against acceleration. You settle into an ordinary seat in an ordinary cabin, and the first strange thing is the announcement. There will be no countdown, no ignition, no roar. There is nothing to brace for. At the appointed moment, machinery you never see begins to shape the energy of the bubble wall far outside the hull, and space around the ship starts to flow, and you feel absolutely nothing. This is the first truth of warp travel, and it may be the deepest one. Inside the bubble, you are not moving. You never will be for the entire journey. There is no acceleration pressing you into the seat because your little pocket of space is flat and calm, and you are in free fall within it, the gentlest state of motion the universe offers. A cup of tea on the armrest does not ripple. A coin stood on its edge on the table stays standing from departure to arrival. Outside, the bubble is already crossing distance faster than any signal in history, and inside, the silence is so complete that you can hear your own heartbeat. The most powerful journey ever undertaken by our species, and it is, from within, indistinguishable from sitting still in a quiet room at night. You have done harder traveling in your sleep. Your watch ticks normally. This still astonishes physicists a little. In ordinary fast travel, relativity charges its famous tax. A traveler moving near light speed through space ages slowly and returns to find the world older than they are, friends gone grey, decades spent in what felt to them like months. But you are not moving through space, and so the tax is never assessed. Your clock stays in step with the clocks back on Earth, tick for tick, all the way across the interstellar dark. When you come home 10 months older, Earth will be 10 months older too. Warp travel does not just spare your body the violence of acceleration, it spares your life the violence of time. No one grows old behind your back. The bubble carries you and your childhood friends and your place in the world all at the same pace. Now go to the window, because this is where the journey stops being restful and becomes something else. You are crossing space at 10 times the speed of light. What do you see? Ahead, almost nothing. The view forward is a darkness with a strange jeweled quality. Light from the stars ahead struggles to enter the bubble at all, and what does get through arrives warped and compressed, shifted toward colors your eyes cannot hold, gathered into a tight, distorted ring around the direction of travel. Calculations of the view from inside an Alcubierre bubble describe the sky ahead crushing inward, the familiar constellations smearing and sliding backward, as if the universe were being folded shut in front of you, behind the opposite. The light of everywhere you have been stretches and reddens and fades like embers cooling on the hearth of the sky. You are wrapped in a cocoon of curved light, sliding between two darknesses. Travelers will someday cross entire star systems without ever seeing them go by. And even at this speed, the universe insists on teaching you its scale one last time. 10 times the speed of light sounds like omnipotence. Watch what it actually buys. The moon, which took the Apollo astronauts 3 days, goes by in a seventh of a second. Mars passes within 2 minutes of departure. In a little over 2 hours, you cross the distance that took Voyager 1 nearly 50 years, and slip through the boundary where the sun's wind gives way to interstellar space. And then nothing happens for weeks, because beyond the planets lies the Oort cloud, the sun's vast halo of sleeping comets, stretching perhaps a light year or more in every direction, and even at 10 times the speed of light. That outer wilderness of our own home system takes more than a month to cross. Most of your 5-month crossing to another star is spent leaving and arriving. The gulf between the two shores, the part that looks widest on every map, flashes past in the middle weeks, while the quiet suburbs of each sun go on and on and on. Even with the universe's own trick in our hands, the distances do not become small. They only become survivable. Space stays vast. We just stop being brief. And here, at the window, staring into that folded dark, you meet the first of the bubble's shadows. You cannot see where you are going, not because the glass is small, but because of something written into the geometry itself. The front wall of your bubble is causally disconnected from you. That is the formal phrase, and it hides something eerie. Space just ahead of the ship is contracting faster than any signal can cross it, which means no message from inside the cabin, no command, no cry can ever reach the forward wall of the bubble to change its course. Whatever instructions the bubble was given at departure are the only instructions it will ever have. You cannot steer, you cannot slow down, you cannot stop. From the moment the field forms, you are not a pilot. You are a letter, sealed in an envelope addressed by someone else, and the universe is under no obligation to deliver you gently. Physicists have known this from the earliest years, and their proposed solutions only deepen the strangeness. Perhaps the deceleration is scheduled in advance, wound into the field like a music box, so the bubble opens itself on arrival. Perhaps the route must be prepared ahead of time, a corridor of pre-arranged space-time laid down by slower-than-light machines that crawl to the destination first, over decades, building the road that the bubble will one day ride in months. In that vision, humanity's first warp route to Proxima Centauri begins with an old-fashioned crossing, 70 years of patient robots laying track through the dark, so that afterward, forever, the trip takes 5 months. Every road, even this one, has to be walked once before it can be ridden. There are darker shadows still, and since you are drifting towards sleep, I will speak of them the way one speaks of storms that may never come. In 2009, 3 physicists, Stefano Finazzi, Stefano Liberati, and Carlos Barcelo, examined what quantum fields do inside a warp bubble in flight, and found that the bubble's walls behave like the horizons of black holes. Horizons leak. They glow with faint quantum fire, the radiation Stephen Hawking discovered, and inside a superluminal bubble that glow may not stay faint. Their calculations suggest the interior could flood with radiation climbing without limit, hot beyond any material's endurance, a temperature written as a 1 followed by 32 zeros. And the wall itself may be unstable, inclined to collapse the moment quantum effects are counted honestly. Then, in 2012, a team at the University of Sydney, led by Brendan McMonigal, found something almost poetic in its menace. A warp bubble crossing the galaxy does not cross empty space, because space is never quite empty. Every stray hydrogen atom, every grain of dust, every wandering photon the bubble sweeps through gets caught up in the field, gathered and compressed at the bubble's leading edge like snow before a plow, blue shifted to ferocious energies. The bubble carries this gathering storm mile after light year, growing. And when the ship finally slows and the field releases, all of it discharges forward in a single burst, a spray of high-energy particles aimed precisely at the destination. The paper's conclusion has become quietly famous among physicists. Anyone waiting at the arrival point, it says, would be blasted into oblivion. The first starship might announce itself to a new world the way a storm announces itself to a coastline. Arrival, it turns out, is the hardest problem of all. Any civilization that masters the warp bubble must first master the art of stopping softly, of setting the snow down, of arriving the way light arrives on a windowsill. None of these shadows, you'll notice, is a wall. Each one is a problem, specific and nameable, the kind that engineering has spent 3 centuries learning to file down. The radiation depends on the bubble's structure, and newer, positive energy designs may not share it. Their walls may be gentler things than horizons. The arrival burst can be aimed at nothing, discharged into empty space short of the destination. The steering problem may yield to scheduled fields or laid corridors, or none of them may yield at all, and the bubble may remain forever a beautiful solution that physics permits and nature declines to build. Tonight, no one on Earth knows which. But notice where we are. We are debating the radiation shielding and the braking procedure and the docking etiquette of faster-than-light ships. That is not the conversation of a species locked in a glass room. That is the conversation of a species reading the fine print on the key. Still, Since we have come this far together, let's allow ourselves the ending. The physics has not yet earned. Let's imagine the arrival done right by whatever descendants solve the braking and the steering and the storm at the bow. Stay a passenger a little longer. You are 5 months out from Earth, and somewhere ahead, machinery you will never see begins unwinding the field, gently, the way these things are done by then, discharging the gathered radiation harmlessly into an empty quarter of the system, hours before arrival. The folded darkness outside the window relaxes. The crushed ring of starlight ahead loosens, spreads, unfurls back into individual stars, like a fist opening. And then the bubble is gone, and you are simply in space, in the ordinary, honest, sublight universe. And the window is full of a sun that is not yours. Proxima Centauri is a red dwarf, a star so small and so dim that no human eye has ever seen it unaided, even though it is the closest star that exists. From your window it burns the color of embers of copper of the last hour of a campfire, and there is a world here. We have known that since 2016. Tonight, in your bedroom, this is not speculation. Proxima b is real, a planet at least as massive as Earth, circling that ember sun once every 11 days, close enough in to sit in the temperate zone where water, if it has any, could stand as liquid. It almost certainly keeps one face turned always toward its star, the way the moon keeps one face toward Earth, which means that somewhere on that world there is a line, a terminator, a permanent boundary between a day that never ends and a night that never began. An eternal sunset, thousands of miles long, circling the planet like a ring of amber. If human beings ever stand anywhere on that world, they will likely stand there in the sunset country, under a sky where the sun never moves, and the shadows have not changed since before there was an Earth. 4.24 light years. 73,000 years by the ships we have, 5 months by the geometry we can almost write down. And as you hang there at the window, watching an alien sunset that never ends, the thought that finds you is not about engines at all. It is that the light now falling on your face left that small red star before you boarded and beat you here by only a few months. You nearly kept pace with light itself, and you did it without ever moving, sitting still in a quiet room, exactly as still as you are lying right now. Hold that image a moment, the ember light, the standing shadows, the stillness. Then let it go, gently, because we have to come back, and there is one more door in Einstein's equations that deserves to be opened tonight before we close them all, because the warp bubble, it turns out, has a sibling. Einstein's equations contain a second legal shortcut to the stars, older and stranger than Alcubierre's, and the two illuminate each other so perfectly that no honest telling of tonight's story can leave it out. In 1935, Einstein himself, working with his colleague Nathan Rosen, discovered that the mathematics of curved space-time permits something astonishing. Two distant regions of the universe can, in principle, be connected directly through a kind of throat in the geometry, a passage that does not cross the space between because it goes under it. They were not thinking of travel at all. They were chasing a technical question about particles. But the structure they found, the Einstein-Rosen bridge, is what every child now knows by its friendlier name, a wormhole. Picture the old image because it remains the best one. Space is a sheet of paper, and your destination is a mark on the far side of the page. You may cross the page, and the page's rules will bind you the whole way. Light speed, decades, centuries, or the page may fold until your mark and your destination nearly touch, and a single pinhole through both layers becomes a doorway. Step through, and you have traveled light years without moving through more than a few feet of space. Einstein's speed limit is not broken. It is not even inconvenienced. You never went fast, you went around. For half a century, the wormhole stayed a mathematical curiosity because the original version slammed shut faster than anything can cross it. Then, in the mid-1980s, it was dragged into serious physics by, of all things, a novelist. Carl Sagan was writing his novel Contact, and he wanted his heroine to cross the galaxy in a way a physicist would not laugh at. So he called one, and it happened to be Kip Thorne, one of the great relativists of the age, who would later win the Nobel Prize for his work on gravitational waves. Thorne took the question seriously. In fact, he assigned it, and in 1988 he and his student Mike Morris published the answer. Yes, a wormhole can be held open, made traversable, made safe enough that a human being could walk through and survive. The Morris-Thorne wormhole is a fully legitimate solution of general relativity, exactly as legal as Alcubierre's bubble, and it was born the same way, a piece of fiction asking physics a sincere question, and physics, after checking, declining to say no. But there was a price, and by now, deep into tonight, you will recognize it like an old acquaintance. To keep the throat from collapsing, the wormhole must be threaded with matter whose energy is negative exotic matter, the same impossible ingredient the warp bubble demanded, needed here for the same deep reason. Both machines ask space-time to hold a shape it does not want to hold, and the only thing in the universe's ledger that can prop such shapes open is energy below zero. The same Casimir whisper in the laboratory, the same quantum rules rationing every borrowed drop. Two utterly different doors to the stars, discovered decades apart by different people chasing different dreams, and when the toll was computed, it was the same toll. When that happens in physics, it usually means you have stopped learning about machines and started learning about the universe. The message reads like this: shortcuts exist. Geometry permits them. But the collateral is a substance reality barely issues, as if the universe were willing but not eager. And the parallel runs deeper still into the darkest part. Because a traversable wormhole, like a warp drive, turns out to be a time machine in waiting. The recipe is almost embarrassingly simple, and Thorne's own group published it within months of the wormhole paper. Take one mouth of a wormhole on a fast, relativistic journey while the other stays home, and relativity's time dilation will slide the two mouths out of step with each other, so that entering one and exiting the other becomes a journey into the past. The same disease, caught the same way, through the same loophole of faster-than-light connection. It was, in fact, exactly this discovery that provoked Hawking to propose chronology protection in the first place. The universe's two known back doors both open onto the same forbidden room. Whatever stands guard there, and we will come to it in a moment, guards them both. Before we do, though, one gentler branch of this family deserves a mention because it may be the first to bear fruit, and almost no one outside the field has heard of it. The same researchers who built the positive energy warp solitons have pointed out something lovely. A warp structure does not have to carry a ship to be revolutionary. It could carry a signal, a microscopic soliton, a wrinkle of sculpted space-time with nothing inside but information, would be to the starship what the telegraph was to the railroad, immeasurably easier to build and transformative all by itself. Recent papers have worked through what hyper-fast communication inside general relativity might require, and the energies, while still enormous, are a whisper compared to anything crude. If the warp story of the next century has a first chapter, it may not be a ship at all. It may be a message, a single pulse crossing the gulf to a colony ship, or a distant probe in days instead of years. The first artificial thing ever to take the universe's own shortcut. Somewhere between the impossible starship and the patient photon, there is a smallest possible thing that can be sent around the speed of light. Finding it is, quietly, one of the more interesting engineering questions ever posed. Hold the two siblings side by side one last time, the bubble and the bridge, because together they answer a question that the bubble alone could not. One strange solution might be an accident, a defect in the mathematics, a loose thread on the edge of Einstein's carpet. Two independent solutions arrived at from opposite directions, agreeing with each other about what is possible, and agreeing about the price is not an accident. It is testimony. General relativity, the most precisely confirmed description of space and time our species has ever produced, says in at least two separate places that the geometry between here and the stars is negotiable. The universe built its walls with doors in them. It locked the doors and it hid the keys, and it may have posted a guard we cannot see past. But it built the doors. And you do not build doors into a prison you intend to be eternal. And yet, after all of it, after the shrinking energy bill and the positive energy solitons and the physical warp shells, there is one more problem. It is quieter than the others and deeper, and it may be the real reason the universe drives so hard a bargain. The problem is not distance or energy or radiation. The problem is time. Because a true faster-than-light machine of any design in any century is also automatically, unavoidably a time machine. That is not a figure of speech. It is a theorem of relativity, and it deserves to be unfolded slowly here in the dark, where strange things are easier to look at. Start with a question that sounds trivial. What is happening on Proxima Centauri right now? It feels like that must have an answer. Somewhere out there, this very instant, something is or is not occurring. But one of the deepest lessons of Einstein's relativity is that the word now does not reach that far. Now is a local possession. For distant places, the universe simply does not maintain a single master clock, and different observers, moving at different speeds, will disagree about which faraway events are simultaneous with this moment in your bedroom. They are not confused, and they are not wrong. Each one's version of now is as valid as every other's. Relativity's full name is the relativity of simultaneity, and for 120 years that strangeness has stayed politely out of human affairs for one reason only: nothing can travel fast enough to make the disagreement matter. The speed of light is the referee. As long as no signal outruns light, no observers now can ever be caught contradicting another's, and history unfolds in the same order for everyone. If you want to feel how deep the strangeness already runs, even without any starship, there is a famous thought experiment about it, sometimes called the Andromeda paradox, explored by the physicist Roger Penrose. Two people pass each other on an ordinary sidewalk, one strolling toward town, one strolling home. Because they are in motion relative to each other, their planes of now stretched across the universe tilt by a tiny angle. Over the width of a street, the tilt means nothing. But project it out 2.5 million light-years to the Andromeda galaxy, and the two strollers' versions of what is happening in Andromeda right now can differ by days. For one of them, now in Andromeda might hold a fleet of ships still deciding whether to launch. For the other, walking the opposite way past the same lamppost, the launch may already be part of history. Neither is wrong. At walking pace across that distance, the disagreement is already that large, and nothing about it causes any trouble, because no signal, no influence, no consequence can cross the gulf faster than light to make the disagreement bite. The speed limit is what keeps all these tilted nows from ever being compared. Light speed is not really a rule about motion at all. It is the universe's filing system, the thing that keeps every observer's story consistent with every other's. Give someone a warp bubble and the filing system fails. The referee leaves the field. Here is what the mathematics says, stripped of its machinery. A ship that crosses space faster than light is crossing between events so quickly that, for some perfectly legitimate observers, it arrives before it departs. Not appears to. Does. And that is still survivable barely as long as only one ship is involved. The true catastrophe needs two. Send a warp ship out to a distant star and have it immediately turn around and warp home, timing things against an observer moving just so. The mathematics is unambiguous about what becomes possible. The ship can arrive back at Earth before it originally left. The crew could stand on the landing field and watch their own departure. They could radio the launch tower and cancel the mission they are currently returning from. Physicists call the setup by an old and wonderful name the tachyonic anti-telephone, the telephone that lets you answer before anyone calls. An effect could precede its cause. A message could arrive before it was sent. A traveler could, in principle, prevent their own trip, and then the universe would owe an explanation for a returning ship whose journey never happened. This is not a paradox of engineering to be filed down like the radiation or the steering. It is a paradox of logic. And notice now something beautiful about the universe's own faster-than-light behavior, the expansion you learned about hours ago. Galaxies receding beyond light speed can never loop back. Their superluminal separation carries them apart, outward, away, into silence. Light from them fades. No message returns. The universe's version of the loophole is, by its very shape, incapable of ever sending anything into its own past. The cosmos breaks the speed limit only in the one direction that keeps history safe. It is as if the exemption were written with a lawyer's care. Expansion may exceed light speed, provided nothing ever comes back. What the warp bubble proposes is the missing forbidden half, FTL that returns, FTL that answers, and it may be exactly that half, and only that half, which the universe cannot allow. Stephen Hawking took this possibility seriously enough to give it a name. In 1992, he published what he called the chronology protection conjecture, the proposal that the laws of physics conspire always and everywhere to prevent closed loops in time from ever forming. Whenever a space-time bends close to permitting one, Hawking argued, quantum effects surge at the critical boundary, piling up energy that destroys the doorway at the very moment of its creation. The universe, in this view, has an immune system against paradox. Hawking, being Hawking, gave the idea a joke to travel with. The conjecture, he wrote, would keep the universe safe for historians. But underneath the joke sat a conjecture he could not prove, and no one has proven it since. It remains exactly what he called it, a conjecture, a suspicion about the universe's character, drawn from decades of watching every candidate time machine, wormholes, spinning cosmic strings, warp bubbles, die of its own mathematics just before the loop closes. Every single one, so far, self-destructs. It may be a coincidence of the examples we have tried, or it may be the deepest law we have ever glimpsed, deeper than the speed limit itself, the law the speed limit exists to serve. And there, I think, is the real shape of the thing we have been circling all night. The speed of light was never the point. It was never the treasure being guarded. What the universe appears to protect, with infinite energy walls and horizon fire and conjectures that hold against every assault, is the order of cause and effect. The sanctity of the one-way flow from what happens to what happens next. The speed limit is just the fence. Causality is the garden, which reframes our whole predicament in a way I find strangely hopeful, and I want to offer it to you before we drift toward the end. If the universe's true law is not thou shalt not go fast, but thou shalt not undo what has been done. Then there may be enormous room inside that law. Warp bubbles that cruise below light, speed violate nothing, and one already exists on paper, made of honest, positive energy. Warp corridors that run one way out into the dark, with no return faster than light, may thread the needle entirely, delivering the stars without ever threatening a single yesterday. The universe has not said no to the engine. It has said, perhaps, no loops. And a species that wanted the stars badly enough could live inside that clause forever, and never once feel its walls. Before we come to the end, I want to step away from the equations for a while and talk about the word impossible itself. Because our species has a history with that word, a long and humbling one. And if you only remember one thread from tonight, this one would serve you well on many nights to come. In 1895, Lord Kelvin was perhaps the most celebrated physicist alive, president of the Royal Society, the man whose name we still attach to temperature itself. And around that time he is famously said to have declared that heavier than air-flying machines are impossible. Whatever his exact words, his skepticism was real and documented. He had no faith in flight, and he said so, and he had earned the right to be listened to. He understood energy and matter more deeply than almost anyone who had ever lived. 8 years later, on a cold beach in North Carolina, a bicycle mechanic lay flat on the wing of a machine built of spruce and muslin and flew. The experts did not merely fail to predict flight, they failed at the 11th hour with the answer already assembled in a shed. On October the 9th, 1903, the New York Times published an editorial titled "Flying Machines Which Do Not Fly." A respected government-funded flying machine had just dropped itself into the Potomac River, and the editorial drew the reasonable lesson. It calculated that flight might be achieved eventually by the continuous effort of mathematicians and mechanics in somewhere between 1 million and 10 million years. 69 days later, the Wright brothers flew at Kitty Hawk. Not a million years. 69 days. The margin by which the smartest analysis of the age missed the future was 99.9999%, give or take. And there was no announcement, no headline the next morning. The world simply did not notice for years that the impossible had quietly become a fact in the wind. It happened again, and this time the target was space itself. In January of 1920, the New York Times turned its attention to a physics professor named Robert Goddard, who had suggested that a rocket might one day reach the moon. The editorial did not merely doubt the engineering, it corrected his physics, in print, with magnificent confidence. A rocket, the Times explained, could not possibly work in the vacuum of space because there would be nothing for the exhaust to push against. Professor Goddard, it said, seemed to lack the knowledge ladled out daily in high schools. Every word of that correction was wrong. The rocket pushes against its own exhaust. Newton had settled the matter 3 centuries earlier. Goddard knew it, high schoolers knew it, and the editorial page did not. The Times finally published its correction on July 17, 1969, 3 days before human beings walked on the moon, with a dry little sentence that has become legend. Further investigation and experimentation have confirmed the findings of Isaac Newton. The Times regrets the error. 49 years from mockery to apology, and the apology arrived while the impossible thing was actually in flight, halfway to the moon, carrying 3 people. I am not telling you these stories to sneer at the doubters. That would miss the point entirely, and the doubters were often the best minds of their day, reasoning honestly from the physics they had. I am telling you because the pattern has a shape, and the shape matters tonight. In every case, the wall between possible and impossible turned out to be made of 2 different materials, and nobody could tell them apart from a distance. Some walls are laws of nature. Perpetual motion really is forbidden, and no amount of Kitty Hawk spirit will ever unforbid it. But other walls are only engineering, only ignorance, only the absence so far of the right trick, and they look identical to law right up until the morning someone walks through them. The whole art of prophecy in science is telling the 2 apart, and our species has been reliably, repeatedly, gloriously bad at it. So the honest question, the one worth carrying towards sleep, is which kind of wall the speed of light is. And here tonight's story earns its strange optimism, because we already know the answer, and we have known it since before your grandparents were born. The light barrier, as a wall against motion through space, is real law. It will never fall, not to cleverness, not to power, not in 1 billion years, and every physicist alive would stake the field on it. But the universe itself showed us, in the recession of the galaxies and the fury of inflation, that the wall has always had a gate, and the gate is not against the law. Space may carry what space contains, at any speed it likes. Alcubierre found the gate shape in the mathematics in 1994. 30 years of haggling has been the sound of our species learning what the toll might be. The remaining questions, the energy, the stability, the steering, the arrival, the loops in time, are enormous. But they are questions of the second material. They are engineering and ignorance, prices and tricks. And prices and tricks are the exact category of wall that 69 days once reduced from 10 million years to a beach in December. There is one more number worth holding up against the dark, and it is my favorite one, because it is about us. Modern physics is young, almost embarrassingly young. From Maxwell's equations of light to the Wright Flyer was about 40 years. From the Wright Flyer to the moon was 66. One human lifetime, one stretched from the first powered flight to boot prints in lunar dust. Einstein published relativity 120 years ago. Alcubierre's paper is barely 30 years old. Lenz's positive energy solitons are not yet 10. The first fully physical warp solution was published last year by the standards of tonight's story, moments ago. We are not a species at the end of a long failed pursuit of the stars. We are a species in the first minutes of it, still reading the problem, and already the price has fallen from 100 billion universes to a question about plasma engineering. Nobody knows how this story ends, but it would take a brave editorial writer knowing our history to publish the piece that says never. So what happens next? Not in the someday of starships, but in the actual years ahead, in the journals and laboratories where this story is currently being written. The honest answer is quieter than a launch, and I find it more comforting. The first thing that happens is software. It sounds anticlimactic, and it is the opposite. For most of the warp drive's life, checking a new bubble design meant months of specialist mathematics that only a handful of relativists on Earth could perform, and mistakes could hide in the algebra for years. That era just ended. The team at Applied Physics released Warp Factory, a numerical toolkit that lets researchers build a candidate warp geometry inside a computer and interrogate it ruthlessly, mapping exactly where energy must sit, testing every energy condition point by point, the way an engineering firm stress tests a bridge that exists only in blueprints. Other groups now run independent verification codes of their own, and they check each other's claims, and sometimes they catch each other's leaks, tiny hidden patches of negative energy in designs that claimed purity. This is what a field looks like when it stops being a curiosity and becomes a discipline. Aviation had wind tunnels before it had airlines. Warp physics just got its wind tunnel. The second thing that happens is the slow, deliberate pursuit of the subluminal warp. Remember what the 2024 result actually established. A bubble of sculpted, ordinary, positive energy can carry a pocket of flat space through the universe below light speed, with passengers inside feeling nothing. No acceleration, no strain, no time slippage beyond the ordinary. Set aside the stars for a moment and think about what even that machine would mean. The hard ceiling on every rocket we have ever flown is propellant, the brutal arithmetic of carrying the fuel to push the fuel. A warp shell does not push. Its speed is written into geometry, not burned into thrust. A crude craft that could hold even a few % of light speed steadily would put Mars a weekend away and Pluto inside a month, would make the outer solar system a coastline instead of an abyss, and would do it with the passengers riding in the stillness of freefall the whole way. No bone loss, no crushing burns, a cup of tea unrippled on the armrest. Interstellar distances would remain long, but they would fall from the scale of civilizations to the scale of institutions. At 1/10 of light speed, Proxima Centauri is a 40-year crossing. One working lifetime, the same span the Voyager probes have already been flying. The generation ship problem, everyone who boards will die aboard, quietly becomes the research posting problem. And nothing in that entire paragraph requires a single gram of exotic matter or offends a single energy condition. That is the floor this field is now standing on. The floor, not the ceiling. And the energy figures, enormous as they remain, live in exactly the part of the story that has always moved. The published estimates for meaningful warp shells still involve masses and energies on planetary scales, numbers that make engineers laugh and then go quiet. But those numbers are the direct descendants of a figure that began at 100 billion universes. Every single decade since 1994 has shaved orders of magnitude off the price, not through new physics, but through better geometry, better shaping, better questions. There is no theorem anywhere that says the price stops falling. There is only the historical fact that it has never yet stopped falling, and a research community, growing yearly, employed in continuing the descent. The third thing that happens is the deepest one, and it may matter more than any starship. Warp research has become one of the sharpest tools we have ever held for asking what space-time actually is. Every warp geometry is a question posed directly to general relativity and quantum mechanics at once, the two great theories that famously refuse to speak to each other. The bubble walls that behave like horizons, the quantum fire that may flood the interior, the conjectured immune response that protects chronology. These are not engineering nuisances. They are the exact places where our two best descriptions of reality grind against each other. And physics has always made its largest leaps at exactly such joints. It is entirely possible that the warp drive's true destiny is not to carry anyone anywhere, but to be the question that finally teaches us what space and time are made of. The universe has been asked few better questions, and it would be very like the history of science if, in taking the door apart to see whether it opens, we discovered what the whole house is built from. Somewhere in all of this, there is a version of the future in which none of it works. It deserves to be said plainly, once, without flinching. Perhaps chronology protection is absolute and the instabilities are incurable, and the energies never fall within reach and the bubble remains forever a mathematical bird that cannot survive real weather. Even then, notice what would remain. The subluminal shells, the propellantless cruising, the physics learned at the horizon walls, and above it all, a sky that still, forever, performs the original miracle every night. Galaxies riding expanding space beyond every limit, the proof of principle written in 100 billion star letters across the dark. If we never learn to do what the universe does, we will still live inside the demonstration. The loophole does not need our permission to be real, and the wall does not grow back just because we are slow. But the other version of the future is also still alive, and no honest referee has yet ruled it out. The version where some graduate student not yet born, running a geometry not yet tried in software, not yet written, watches the last energy condition go green and the last leak close. The version where the 69 days arrive. Nobody standing in 1903 could see Kitty Hawk from the editorial desk. Nobody standing here can see whether that morning is coming or when. What we can see tonight from a small planet from under warm blankets is that the question has survived every attempt to kill it for 30 years, that the price falls every decade, and that the universe, which could have said no, keeps saying, instead, the strangest and most patient word in physics, perhaps. Now, as we finally come to the end of tonight's journey, let the equations dissolve and keep only the shape of what happened here, because underneath the physics, tonight was a story about a species and a wall. For nearly all of human history, we did not even know the wall existed. We looked up at the stars and thought them close. Lanterns hung just past the mountains, close enough that the gods commuted. Then we learned to measure, and the truth of the distances arrived like cold water. Then we learned relativity, and the truth became a verdict. The stars are unreachable, not by accident of engineering, but by decree of nature, and the 20th century largely accepted the sentence. And then, patiently, in the way our species always does its finest work, we kept looking anyway. We watched the galaxies and caught the universe itself ignoring the speed limit in every direction. We reread the decree and found it never said what we thought it said. We found the gate, we measured the toll, and for 30 years now, we have been standing at that gate doing the most human thing there is, arguing about the price, in public, in mathematics, with the lights on. Think of what was handed forward to bring you this one bedtime story. Lemaitre saw the growing universe inside equations their own author distrusted. Hubble measured the leaning sky. Guth found the first morning's fire. Alcubierre, watching television after work, asked the child's question in the adult's language and refused to be embarrassed by it. Van den Broek folded the price 100 billion-fold with a page of geometry. Lentz found the shapes that need nothing exotic at all. Hawking, from inside a failing body, stood guard over time itself. None of them will board the ship, if the ship ever sails. Every one of them widened the gate anyway. And notice the shape of the gifts they left. They gave us a universe that was larger than we feared, and stranger than we hoped. They gave us a speed limit that turned out to be a filing system, guarding not motion but memory, not distance but the order of our days. They gave us walls with doors in them, and doors with prices on them, and prices that fall. They gave us, above everything, the standing permission to ask. That permission is renewed every time someone checks the impossible instead of bowing to it, and it was renewed again last year, and it will be renewed again next year in papers most of the world will never read on behalf of everyone asleep. That is the inheritance you are lying in tonight, not the starship, the habit. The habit of holding the word impossible up to the light and checking the fine print. The habit that turned 10 million years into 69 days and a newspaper's sneer into a correction printed while the rocket was actually falling toward the moon. The habit is older than physics, and it will outlive every wall, and on the nights when your own life feels fenced in by verdicts, it is worth remembering that this is what the fences have always eventually met. Thank you for joining me tonight on this journey past the speed of light, out to the galaxies that are outrunning it as you breathe, back through the first fire of inflation, and up to the quiet gate that 30 years of stubborn minds have been slowly unlocking. If tonight's journey brought you some rest, or gave your thoughts somewhere vast and gentle to wander, a like or a subscribe helps more of these nights get made, and it means more to this small channel than you'd realize. But that is for the morning. There is nothing more you need to do tonight. So let the numbers go now. Let go of the trillions of miles and the billions of years. Keep just one picture. Above your roof, right now, past the streetlights and the weather, past every star your eyes could ever find. The galaxies are receding faster than light, silently, harmlessly, the way they have every night of your life, every night of everyone's life, since before there were eyes at all. The universe is not waiting behind a wall. It is in motion, hurrying outward, carried on the same flowing space that may someday, some far morning, carry us. The wall was never the whole truth. The gate was always there. And it is very old, and it is very patient, and it will still be there tomorrow. Sleep well tonight. Good night.